Good afternoon, everyone. Thank you for coming out to the talk this afternoon. So Nicholas Roy is going to be is the Bisplinghoff Professor of Aeronautics and Astronautics and a member of the CSAIL community lab at MIT. Today he's going to be talking about some recent work in joint reasoning about semantic representations and physical representations and what these joint representations mean for planning and decision making. He's also going to be talking to us about learning symbolic representations for robots and how to preserve optimality within that. So with that, I'll turn it over to you. Thank you so much for being here.
Thank you very much for the introduction, and it's a pleasure to be here. Thank you, Anka. This is a little bit of a departure of a talk for me, as I've gotten very interested in representations. And of course, learning representations is something that's, there's an entire conference on learning representations. So it's very much a hot topic. But for me, representations have very specific utility. And in particular, I need them to solve a problem that I encounter all the time. And so I'm just going to begin with a little bit of a story about a robot project I had. So in 2015, DARPA awarded MIT and Draper Labs this program, the Fast Lightweight Autonomy program. And the objective was to get a drone to fly around in all kinds of environments relatively quickly and do more complicated tasks than simply fly around. And I'd been working in drones for a little while. And so I was like, okay, we've been addicted to laser rangefinders for far too long. We are going to try and do this entire task with using a single forward-facing camera. And that, a single forward-facing camera is not a particularly useful solution for many reasons. And this isn't going to be a talk about making a drone do things with a single forward-facing camera. But it is instructive to think about what we were actually doing with the camera as we were flying around in this urban environment. For instance, with a single forward-facing camera, monocular slam is now good enough that you actually can build, maybe not, this is, a lot of computer vision people will look at this and say, this is absolutely horrible, you're embarrassing yourself. But the point is, it's actually good enough to see the buildings and not hit them, which is kind of all you want when you're a drone. But it's a very granular, detailed representation that captures the geometry very coarsely, but doesn't do a whole lot else for you. The mission in this case was to actually fly around in this environment and localize objects of interest. So, there's the military application, but there's also the civilian application, which is easier to talk about. So imagine that you're Liberty Mutual, and this is a real example, and you want to locate where all the people, Liberty Mutual is a big insurance company. They come in after disasters like hurricanes or floods, and they often need to know where all the assets are that they were insuring, such as cars. And so in this particular case, our quadrotor was told to fly around in this section of this urban environment and locate all the cars. And we actually were able to produce a map that had locations of the buildings and actually had the labels of these relevant objects, et cetera. And this worked relatively well for us, except when it didn't. And it's instructive to think about when it didn't work. So let's think about pretty much every operational robot system on the planet. That there is relatively close to the sensors and the actuators a fast duty cycle control loop. There's sensors providing data to an estimator, common filter, graph-based SLAM optimization system, what have you. This is producing an estimate of the vehicle's position and maybe in a coordinate frame relative to some goal. The motion planner takes in the coarse geometric model I showed you, and it produces a motion plan and gives that to a controller that then executes that and motors, and off we go. And this works reliably. This is your self-driving car. This is inside your DJI vehicle, et cetera. But this basically is only good enough for getting a vehicle from point A to point B in some configuration space. When you want to do any kind of higher level task, and you're always doing some kind of higher level task, typically what we do is that we have some kind of symbolic state extraction that kind of represents our progress in some kind of task plan. That symbolic state is given to some kind of symbolic planner that's reasoning at a much higher level than the physics and the geometry, and then a sub-goal is given to the motion planner if things need to change. And this is the thing that always breaks. Why is this the thing that always breaks? Well, it's not actually, this thing works relatively well. What always happens is that the relationship between what's happening in the low-level geometry and the high-level task plan, this is the part that always goes wrong. Why does it go wrong? Well, here what I've done is I've circled all the arrows that represent or the information flow conditioned on some kind of model where we're able to learn the model from data. So we can use system identification to learn a model of for our estimator. We can use system identification to learn a model of our plant for our controller. We can even learn how our estimator says what our motion plan should do. This is probably a slam loop. The motion planner can have some kind of optimization strategy that allows it to give meaningful things to the controller. All of this stuff works great, and it works great because the models are learned from data. We can even do the same thing up here with our symbolic planner. We can learn, reinforcement learning has many things to say about this, and we can drive our vehicle around through many plans and actually learn this relationship. But there's two arrows that I can't circle in green because I can't learn them from data. These two here. I can't learn a relationship between an estimate in some kind of ECF coordinate frame and some kind of symbolic state about what part of the street the vehicle is in. Same thing as I can't necessarily learn the relationship between like go home and a subgoal and some coordinate frame to give to the motion planner. So what do? We always end up hand coding this relationship. There's some snippet of Python or C++ in your vehicles that basically does this sequencing. We call this engineering by grad student or engineering by software engineer. And this is not, all of our vehicles have this. And the problem is this thing gets arbitrarily complicated. This is a software architecture map from a software system for a mobile robot for an army project I happen to be on. And the different boxes correspond to different subsystems. And if we zoom in on the action subsystem right here, we see things, high-level symbolic actions like search or go to, navigate, observe. And you'll notice there are people's names under those capabilities. That's because those are the people who wrote those. And this all works well and good until Bob goes to work for Uber, and then what do you do? True story. So the reason we do this, the reason that we live in this unhappy state of affairs is we don't actually know what is the optimization problem that allows us to actually learn or derive automatically the relationship between our low-level geometry and our high-level representation. Why do we have this high-level representation? Why do we even have to do this? The reason we do this is because this is an abstraction over our position in the world, and the symbolic actions are abstractions over things we want our motion planner to do. So we understand that we need this because we need abstraction in order to be able to plan efficiently. If we had to plan the entire day of a self-driving car at this level, we couldn't, right? We know that motion planning is B to the D, and if the D is the length of your working day, you need more computing than you're going to have access to. And so we need the abstraction, the computational efficiency that this gives us, but we don't have a definition of what actually represents not only a good abstraction, but even a complete abstraction. And so the questions that I wanted to answer, I basically gave my research group a challenge 3 years ago. It was like, let's figure out what makes a good symbolic representation, and let's figure out how to learn the relationship between these. And so I'm going to start, just with that first question. What makes a good symbolic representation? And I'm going to immediately leave the world of drones and self-driving cars and go to the simplest dynamic system that we can think of. And I want to acknowledge this is work that I've been doing with my grad student, Will Vega Brown, who some of you may know. And so, this is really his insight. So I'm going to imagine that I have a very simple one-dimensional environment, which is a ring. And I have two robots, an R robot and an O robot. And I want to put them in, and so the R robot and the O robot occupy a particular position in the environment, x-axis position of the R robot, y-axis position of the O robot. And so I want them, for instance, to swap places. And so this is a very easy motion planning problem to give them. The motion plan that looks like this is going to be one of the robots moving to this position. The other one robot has to go the long way around. And this is what the plan looks like in configuration space. This gray bar is blacked out here. This is kinematically infeasible part of the configuration space. The robots can't occupy the same part of space. And I can find that motion plan relatively easily using your favorite motion planning strategy, whether it's the RRT over here or the RRT star over here. But this is fully actuated. No problem. What happens if I turn one of the robots into an object? And so now I'm going to call the O robot an object. And so it can't move by itself. It can be moved by pushing, but it has to be pushed. So now the optimal plan, or a plan to solve this is the R robot swings over here, it pushes the O robot into place, which is right there, and it slides back. Now, the plan that solves this now looks like this. The R robot can only, or the system, the entire system basically has to move parallel to the x-axis because that represents only the R robot moving, except when the two objects are in contact. So they're in contact at this point in the configuration space, right at that point where we see the kinematic infeasibility. We slide down the plane of that kinematic infeasibility, pushing the object into place, and then the robot lets go and slides back again. So, fine. This, however, is an extremely difficult motion planning problem to solve. The reason for why it's difficult depends on your perspective in life. Some of you may think of this as a hybrid system, where we have one set of dynamics and then when we are not in contact, and we have a different set of dynamics when we are in contact. Some of you may think of this as a problem because the optimal motion plan goes through a subset of measure zero. We have to be in contact when we slide along in order to push the object, but finding the contact relation can be arbitrarily hard. What is worth noting, though, is that each phase of this problem is relatively easy. So we can think of the system as a piecewise decomposition, or a piecewise analytic system, excuse me. So when the robot is not in contact with the object, it's inside this orange space right here, and the dynamics are super easy. We can solve for any motion planning problem inside there. When the robot is in contact with the object, depending on whether it's on one side of the object or the other side of the object, we have a different dynamical system. Each of those dynamical systems are analytic, but the combination of those, the union of these three systems is only piecewise analytic. And piecewise analytic problems are incredibly challenging. So how do we know? So the first question people often ask is like, well, how do you know if your system is piecewise analytic? How do you actually even know where these sections are? And from a perception standpoint, it's actually relatively hard to know if your system is piecewise analytic. But if you actually have a dynamic model of your system, which you almost always do, then your dynamic model exposes for you the segments of the environment in which you may have different dynamics. And the way we tend to write our dynamics models are almost always a series of switches or if-then-elses between analytic segments of our system. And the number of problem domains included like object rearrangement, manipulation planning, assembly of structures, legged locomotion. Notice that almost all of those are piecewise analytic because they involve contact in some kind. It is easy to construct problems that are piecewise analytic with respect to observations. Those tend to be problems that require planning under uncertainty, so I'm not going to talk about that, but this is not just a problem of contact, but it is easiest and most common to think of this as a problem of contact. And lots of people, as a consequence of the difficulty of thinking about hybrid systems and piecewise analytic systems, kind of gave up on providing optimality or performance guarantees. There are people who I do not think that I have any of them recent. So lots of people at Berkeley have thought about this. This is not an exhaustive list by any means, so apologies if your name should be up here and I didn't get it. But Ken Goldberg's group is here and others as well. Notice that satisfying is just can we find any plan is far and away the biggest list. Optimizing through piecewise analytic systems is incredibly complicated. And that's exactly why we have this symbolic representation at the top, is that we know that we can solve certain kinds of motion planning problems, and so we tend to break it up as best we can and try and solve each of those motion planning problems simply. And what goes wrong is when we miss some of the dynamics. We fail to actually take into account our dynamic model when we're coming up with a symbolic representation of our system. So can we actually do that? Can we actually take build a decomposition of the world in a way that takes into account our dynamics? So from controls literature, there's essentially three modes to our system, three analytic systems. And inside any analytic system, I can't necessarily, inside any one of these modes, I can't necessarily move to an arbitrary place, but I can move to a subset of arbitrary places, so I can have the robot slide back and forth on what's called an orbit. So it's the set of states that are reachable inside any given mode. And that locally accessible space, and I'll define this term accessible more precisely in a few slides. But if I want to get to any point on a mode, I can't. All I can do is really plan to stay inside an orbit. But notice that I can travel to orbits on connecting modes, and maybe I can use a series of orbits to get me from place to place inside this system. And so at this point, the only thing left to do is to say, okay, well, how do I actually make sure that I can get from orbit to orbit, from mode to mode? And here the answer is really up to you. How are you going to solve for the motion planning problem on an orbit? So let's say that I imagine that I'm on this red orbit and I know I want to transition to the blue orbit. How am I going to solve that planning problem? There's lots of different ways to do it. You can, if you're lucky, you can solve it as an optimal control problem by putting a state at the union of these two orbits. Or maybe you're doing random sample motion planning, which is what I'm going to do here. Then all you need to do is to make sure your sampler samples not only from the interior of the orbit, but it also has to sample from the boundaries of the orbit where it touches on other modes. And so that gives us the first algorithm I want to tell you about today, which is the orbital Bellman tree. So I'm going to take a look at my dynamic system, and I'm going to give each dynamic system to my sampler and say, please build me, say, a probabilistic roadmap on this analytic system. And, oh, by the way, please make sure to sample from the boundaries or the intersection of the orbit with adjacent modes. And then I'm going to create an edge between I'm going to build a probabilistic roadmap, and I'm going to create an edge between any two configurations that are close to them some critical distance. Why am I doing this? What this allows me to do is to take advantage of the same proofs of optimality that drive the RRT star. So what I'm actually doing here by doing sampling and actually shrinking the distance between samples that I'm allowed to put in an edge, I'm basically guaranteeing that my probabilistic roadmap is going to converge to the optimal probabilistic roadmap, the PRM star. So I now have a mechanism for randomly building a probabilistic roadmap that basically efficiently transitions through the different analytic modes of my system, guaranteeing that I have a graph at the end that expresses the optimal plan. And so once I have built my graph, I can just do A star, and I have the ability to solve these complex task and motion planning problems, not just guarantee that they are complete, but they're optimal. So I'm no longer at the mercy of somebody actually hand coding my symbolic representation. Little bit of a wrinkle. If I sample the way that I just said, I get probabilistic roadmap, PRM star graph that looks a bit like this. This is relatively inefficient to actually solve. I can be more, but it also doesn't take into account the fact that the object and the robot are actually independent of each other for most of the existence of the system, except on this particular manifold and this particular manifold. So if I actually take advantage of that independent structure and sample the O's and the R's separately in the biggest analytic mode and then only sample them jointly on the low-dimensional modes, then I get a graph that looks like this, and this is much more efficient to sample from. And so now I can solve complicated problems like this. I mean, this is a toy example, but we can do more complicated things. So imagine that I want to put the red box into this red region here. So that's a task planning problem. And I can break it into a series of motion planning problems, such as pushing the red box into here or pushing the green box out of the way, et cetera. If you give this to your favorite task and motion planning problem, you probably end up with a solution that looks like this. And this is not the wrong solution, but it's clearly not optimal. And the reason it's not optimal is because each motion planning problem is solved independently. And there's no way to actually search through the combination of the high-level tasks and the low-level motion plans simultaneously. If you use the factored orbital Bellman tree, you find the optimal plan. And I got to be a little bit careful because, of course, I'm using the PRM star, so it's optimal in the limit of it's asymptotically optimal in the limit of infinite number of samples. But we're able to find this plan here that does the much more efficient thing of moving the green box a little bit out of the way and then pushing the red box in. It's able to find that relatively efficiently. So what we showed here is an algorithm that takes a task and motion planning problem that's expressed by a hybrid dynamic system and basically taking advantage of the hybrid dynamics to break the problem up into distinct pieces or symbols, if you will, that basically can be now solved as one big motion planning problem. And that was really great for us. Then Will asked the question, well, like, what does that actually mean for task and motion planning? We know that motion planning is piece-space complete. We don't necessarily, because we've been at the mercy of like no principled decomposition of task and motion planning problem, we actually did not know what we could say about task and motion planning as a, in terms of its asymptotic complexity or what class of problem it is. So if motion planning is piece-space and we can turn task and motion planning into just emotion planning, does that mean what we might think it means for task planning? So is it possible that we could come up with a definition of our representation that allows us to say that task planning is no more complicated than motion planning? And we're going to use this idea of a stratification. So notice that what I was doing is I was looking for places where my dynamics were analytic. And places where your dynamics are analytic tend to be places where they tend to correspond to chunks of your configuration space where the configuration, the reachable part is of constant dimension. So I can imagine taking this box here and stratifying it into the interior of the space, which is 2D, the boundaries, which are 1D, and then the corners, which are points. And each of these represent sets of constant dimension. Okay, so a control system is accessible if the reachable points have non-empty interior. So notice that accessibility depends on the definition of reachable. So we know what reachability means. It's like, does there exist a sequence of controls that will get me to some state from some other state? And so if the set of states that are reachable is not empty, then we're going to call that accessible. And so essentially what that means is that I have a volume. When I think, if I were to decompose my environment or my configuration space using a striation, pieces of constant dimension, I have to make sure that that the entirety of that space is reachable. This is an example of an inaccessible system where I have a decomposition, but I can only access this point here and this point here, and the interior of that set is not reachable. Okay, it'd be a funny kind of environment. Like you could imagine, you know, if I had like, I don't know, footholds. Where I could basically put my foot here, I put my foot here, but I couldn't put my foot in between. I couldn't actually striate that into the sort of the entire space represented by the interior of the two footholds, because I know that I can't reach the interior of that set. So I know that, so what I'm going to break my environment up into pieces of constant dimension. So I've relaxed the requirement that the dynamics be analytic everywhere. It's just that the system is constant dimension, and I want the interior to be accessible. I want to be able to reach every point in the inside of that striation as well. I need to make the constraint a little bit tighter. We need the size of that interior to be bounded from below. So I need the size not just to be accessible, but I also need the size of that set to be at least 2 sigma. So, you know, this is an example of uniformly accessible, uniformly in the sense that every striation is of a size at least 2, not sigma, excuse me, delta. And here's an example of a system where, like, you know, at some point the interior of the reachable points falls below some volume. But you can imagine why I would want a lower bound on the size of the set that I can reach, because what that means is that I have a lower bound on my ability to actually, I have I guess an upper bound on the number of samples I need in order to actually find the interior of that set. And so if a system, I'm going to define a system as being having uniform stratified accessibility if the size of the reachable points, if I can go up from one strata to the other and the set of reachable points is of some minimum size. So basically I just need the stratification to be of some bounded from below minimum size, and I need to be able to basically reach every point inside that stratification. But if I have that, then we can decide if a plan exists in piece space time. So it's obviously, you know, exponential complexity in time, but what this means is that if you decompose your environment into strata of constant dimension that are lower bounded from below by a certain size, then we can tell if a plan exists or not in p-space. So this, I think, is a really, really useful result for us in that we can tell, for instance, if we can't tell if our decomposition is, maybe I shouldn't say correct, I should say useful. I can't yet tell if the model is useful, but I can tell if it's broken. So I had this problem where we had this symbolic representation, or we all collectively have this problem where a symbolic representation sitting on top of our low-level motion planner sometimes break because it fails to capture an edge decation. It fails to capture, the motion planner sometimes puts the vehicle into a state where it actually can't get to the next symbolic state. These are the kinds of things that break. But if I have a stratification that's uniformly accessible, I know that if I think that I can get from one symbolic state to the other, I'm guaranteed to be able to find, not just guaranteed to find a plan, I'm guaranteed to be able to find the optimal plan subject to the assumptions of PRM star, et cetera. So, yay, we felt very good about this result, that we could now solve these problems. What makes a good symbolic representation, though, so we had a partial answer, which is that decompositions that are uniformly accessible, or maybe more specifically have piecewise analytics, that was good, but not sufficient. So the thing that I didn't tell you is, okay, I had this song and dance about how we like symbolic decompositions, we like abstractions because they should allow us to plan more efficiently. When we ran the factored orbital Bellman tree, that was not what we saw. We saw we could find good plans, but boy, it took a long time. So you can see that the blue is our algorithm, T is just your bog standard task and motion planning algorithm. You can see that it's not finding great plans, that the plans are sometimes as much as twice as bad as the best plans here. Twice as bad a plan, though, comes at the cost of a couple of orders of magnitude additional computational cost. And so this is very, very depressing at this point, is that, all of this work to try and find good representations, and it didn't actually pay out the way that we wanted. But we at least had, so we had a way of finding decompositions for our environment, finding symbolic abstractions that at least preserved our ability to find optimal trajectories and guaranteed completeness. So that's good. Can we actually take advantage of all the work that was going on in hierarchical planning to actually make the decomposition work for us more efficiently? And so we know really what that means is, can we inject information into the planning process that actually guides the search? We know how to do that. We know how to actually inject information in the form of heuristics. So for instance, given this planning problem here, we could imagine using a star heuristic, like shortest distance, and that would grow the trajectory towards the goal. And we like that kind of information. The problem is that most heuristics that you can think of, they're good locally, but they're a bad heuristic globally due to non-convex obstacles. And so if you actually look at what an A-star tree does, given a Euclidean distance heuristic, it really tries hard to find its way to the goal. It keeps trying to get to the goal and doesn't take advantage of the global structure of the space. And that's exactly what the abstraction does, is it gives you some guidance about the global structure that could be used to make the planning process more efficient. So at this point, I feel a little bit like bringing coals to Newcastle, because the thing that we're able to do is to take advantage of an idea from Bhaskar Marty, who was a grad student here with Stuart Russell, and they developed this idea of angelic semantics. And so the key idea of angelic semantics is that we want to bound the cost of any any plan, any primitive plan in an abstract representation, not only from below, but we also want to bound it from above. So this would be the Euclidean lower bound, and then we might have some other upper bound that tells us what is the worst possible cost that we could pay in trying to get, for instance, from this set to this set. These are obviously not striations, but they're easy to draw. So we know from many, many years of experience how to actually encode lower bound heuristics. And so angelic semantics basically rests on the idea that you can order your search by pruning away places where the lower bound of a plan is greater than the upper bound of some other plan. And so lower bounds, easy to get. It turns out that upper bounds are actually not that hard to come by too. So Young's theorem is technically a statement about the bounding radius of a circle between 2 points, but it's basically easy to derive an upper bound on the length of the plan in that space if you're restricted to a convex sec punctured by convex obstacles. So you have to do a little bit of work to put yourself in this state, but you can come up with plans. This, of course, would assume that your vehicle is holonomic. Connectivity and topology say a lot about upper bounds as well. For instance, if topology tells you that these two spaces are disconnected, then the upper bound and the lower bound, for that matter, are going to be infinite. And so, if we were to take our planning, take our striation, and start attaching upper and lower bounds to our actions in the abstract space, then all of a sudden we go from a search tree that grows like this to a search tree that grows like this. And you can see what's happening with the search tree is that it very quickly finds a path through the rooms. And then what happens is I think this is RT, no, it's probably PRM star. The PRM star graph grows sort of around that reference trajectory until it converges to the optimal. So this is an easy motion planning problem, but it's easy to draw. What about more complicated motion planning problems? So imagine that we have a robot in an environment that looks like this, where the robot has to get to the goal, but it also has to get through these doors. And each one of these switches corresponds to opening a particular door. And so if you look very carefully, you see you need to get doors 1, 2, and 5 opened. The switch for door 5 is behind door 4, so you need to get that open. And the switch for door 4 is behind door 3. So in point of fact, you have to open all the doors. And so a relatively easy planning strategy is to simply identify all the reachable doors and turn or switches and open them. But we can actually solve this relatively complicated motion planning problem relatively efficiently. We can, and I'll give you the efficiency demonstration in just a second, but notice that the plan is actually, it opens door 1, and then it goes to switch 3, and then it opens door 4, but it hits switch 2 along the way, and then it comes back to 5, and then so on. And so what it actually does is it allows the motion planner to work out the order in which we hit the switches and the location where we hit them in an optimal manner. So once again, we have a task of motion planning, a relatively complicated task of motion planning, because we have these hybrid states all of a sudden in terms of the doors being opened and closed and whether we've hit the switches. So the state space is now this binary vector of open doors, binary vector of switches, and the robot pose. Very, very hard to solve that as a motion planning problem, but if you actually decompose the environment in the way that I've described and then use the magic of angelic semantics to solve these planning problems, we get great things. And I made the point about efficiency. So if we just give the problem to A star, we see this is see exponential growth. And notice that it's growing exponentially even when I do a logarithmic scale on the x-axis. And if we look at the number of plans expanded, it just goes through the roof. Once we start taking advantage of the decomposition in terms of the analytics and do a little bit of extra pruning to deal with cycles, we get very, very efficient planning process. So hopefully I have now an even better answer. What makes a good symbolic representation? Well, one that preserves the completeness and optimality of, a decomposition that preserves your ability to express all possible plans. It's complete, and it preserves your ability to find the optimal plan. But it's not enough to allow complete and optimal expressivity. We also want to have good upper and lower bounds. So if you have a decomposition of your space that respects the conditions and provides good upper and lower bounds, you have a good representation. So I felt very good about this work for a while, and then I realized that we were still very much at the mercy of the engineer who is coding for us the representation of the robot in the environment. I assumed that everything was known ahead of time. I knew the robot's pose perfectly, I knew the map, I knew all the doors, etc. And it's probably encoded inside a URDF, and they're never wrong, right? So the question was, how can we actually learn the representation between these using perception? And here, full truth in advertising, I don't have a perfect answer. And so if you squint carefully, you'll obviously see some gaps between the elegant theory of a perfectly known environment that allows us to do efficient planning and the reality of real robots. And not for nothing, but all of those algorithms that I talked about, the factored orbital Bellman tree and the angelic semantics, et cetera, are currently working on toy examples. We don't have them working on real robots yet, but we're pushing hard. So, and the reason is a lot of the time when it comes to real robots, you have to deal with the reality of perception and uncertainty. And so I asked the question is like, okay, when it comes to perception, the representation that we're almost always working with is a map of some kind. It's probably going to be an occupancy grid. So the thing that robots are currently very good at, among other things, is building occupancy grid maps. And so the question is like, what do maps actually do for us? Well, they allow us to compute some terms of the Bellman equation for solving motion plans. They certainly allow us to avoid local obstacles. You can avoid local obstacles when you see them, but maps are really good for remembering the local obstacle that you saw a second ago that's now behind you and not turning around and smashing into it. And of course, the maps could divide up our action space into striations. So we could use the map as a representation for deriving that. So the question I asked my group was, can we do this without can we do these three things without resorting to a geometric map? And in particular, can we do these three things without actually resorting to, can we do these three things in an unknown environment where we don't even have a map ahead of time? So at this point, we're transitioning from symbolic representations that allow us to act efficiently in a known environment to symbolic representations that use perception to allow us to act efficiently in unknown environments. Truth in advertising, all of the guarantees that I gave you in terms of completeness and optimality are going out the window. We don't have those guarantees anymore, but we have the ability to still at least behave efficiently. And this is work with my grad students, Greg Stein and Victoria Preston and Chris Bradley, and some of this was presented at Coral last year. But the real reason that I wanted to get away from geometric maps is that my group has largely been addicted to laser rangefinders for the last 15 years or probably even longer. And I really wanted to get off the laser rangefinder and get onto more camera-based optical sensing. And camera-based optical sensing and camera-based optical SLAM has without a doubt come a long way in the last few years. And my vehicles, you saw the video at the beginning of the talk of a drone navigating using a single forward-facing monocular camera. But the representation that these optical systems produce are terrible. And it's really, really hard to know what to do with representations that look like this in terms of identifying striations, et cetera. So my claim is that these kinds of maps are just the wrong kind of representation, again, for actually reasoning symbolically, et cetera. And I'm not by any means the first person to notice this as well. Kostas Danielidis' group at Penn has done a lot of work in semantic SLAM. Lots of other people have started to look at that too. There's probably work here that I'm unaware of. But the point is that these low-level geometric representations are great for not hitting stuff, but they're really not amenable to abstractions and symbolic representations. And if you think about how people navigate the world too, they don't. Yes, we now know about entorhinal cortex grid cells and hippocampal place cells, et cetera, and there is geometry inside the brain. But people, when they reason, at least consciously, about navigation, don't reason at that level of representation. So, and we can do interesting things. So for instance, let's imagine that I'm here standing in this hallway and I'm told to go to some goal. This is an arbitrary problem, but whatever. Told to go some goal that's 100 meters away. I'm faced with two choices, right? I don't reason about trying to walk through the middle of that wall. I basically think about walking down the hallway, and I think about maybe entering that open doorway. And I can even attach estimates of cost to these things. So for instance, if I know that the goal is 100 meters away, then I probably am going to prefer walking down the corridor. There are relatively few classrooms that are 100 meters across that might plausibly contain my goal. So it's likely that if I enter this room, it's not going to work out well for me and I have to come out again. Much better strategy is a hallway, and I might not be able to see the end of this hallway, but it's a plausible guess that there's more environmental structure down here that I can take advantage of. And so I can make reasonable estimates of unlikely to lead to the goal, likely to lead to the goal. On the other hand, if I set the goal as being 5 meters away, then it is likely, like going down the corridor is fairly self-evident to not be a successful strategy, and inside the classroom is likely to be a successful strategy. So when I ask the question, what is the map actually doing for us? It's dividing up our action space into striations was the claim. But can we actually infer high-level actions from perception, and can we actually determine the cost of those actions? And I don't fortunately have as nice, clean an answer for can we infer high-level actions from perception as I did in terms of the uniformly accessible striations. But I've been really inspired by work by Steve Laval from about 15 years ago, where he observed that it was possible for a robot that only had a gap sensor to actually navigate optimally in an environment that did not contain holes. And environments with holes are a whole other thing we can talk about. But I've tried multiple times to get a student to implement the gap navigation tree on a real robot. I haven't given up. You can tell how successful I've been by that statement. I gave this problem to a student near the master's, and he's like, no, this is dumb. And I said, no, I'd really like you to try it. And he's like, no, it's dumb. I was like, just go, please do it. And so he came back 2 months later with a formal proof that it actually could not be made to work on a robot with finite resolution sensing and finite range sensing. So at that point, I had to shut up. And so he went to do, he is now the CEO of Skydio. So you can tell, you can draw your own conclusions about our relative intellect from that little parable. Anyway, what we can do though is actually, one can, not perfectly with no guarantees, extract range discontinuities. These look essentially the same thing as frontiers in the known map. And so we can actually use those gap discontinuities as our action space. Again, no guarantee of completeness, no guarantee of correctness, but we can actually, but they do correspond in some sense to properties of the immediately perceived environment that represent high-level abstract actions. And so we can define these sub-goals as actions, and then we can actually try and compute the cost of following those actions. So we don't have angelic semantics anymore. I'd like to put them back in this work, but we're not there yet. And what we can do is we can try and estimate the expected cost of pursuing actions. And pursuing one of these symbolic actions now is a function of a number of terms. So one is, we have at least a partially known map. We can compute the cost of getting to some symbolic action, sub-goal. That's our first symbolic action. And then we can compute the probability that we will actually continue on from there to reach the goal. And so we can compute the probability that we get to the goal, and what is the likely cost of reaching that goal given everything that has to happen after here. And then we can also compute the likelihood that we fail to get, 1 minus the probability of reaching the goal is the probability we don't reach the goal, and we have some cost of actually failing to reach the goal and then having to turn around and come back. And so this all becomes one big expected cost calculation that's recursive. So when we think about the cost of this action, there's the expected cost of getting to the goal, expected cost of not getting to the goal, having to undo it, and then we'll picking some other symbolic actions. So we have this tree, and we just basically build this tree out to some depth that's determined by the total available computation. The question, of course, is where do these terms come from? The one in yellow we can directly compute from the known map, but the others involve making predictions into the unknown part of the map. And so this being Berkeley, it would be remiss of me not to put up a deep network at least once. And so, of course, we can learn these terms from experience. Because we are still relying very much on geometry and we're not taking into account non-geometric properties of the environment, it's relatively easy to learn these from, for instance, we have all the floor plans of every building at MIT. And so we can train in simulation at MIT and then execute. And so this particular, I forget which building this is, I think it might be building 26, is we get nice emergent properties of the planner. Notice that it does explore a couple of the rooms, but it mostly stays out of the rooms that are far away from the goal because it knows it's not going to make progress there. It took me a long time to remember the answer to the question, which is I had to keep asking Greg and Kristen, why does it go into this room here? And the answer is because it actually saw quite a few rooms that had 2 doorways, and it had a reasonable expectation that it could get a shortcut across here and enter another, and that just didn't work out in this case. But the training data actually indicated that was a reasonable strategy. And then when we compare that to a strategy based on just making guesses about what the unknown part of the space might be. This is an optimistic planner that assumes they can always cut through unknown space regardless of the internal structure, and it just takes a lot longer to get to the goal compared to our nice sort of purposeful planner right here. So those results are with a laser rangefinder, but again addicted to the laser rangefinder. So can we actually do this with a vision sensor? And so we started with mono depth to actually try and, from a flat RGB image, can we recover the depth? And the answer is yes, sometimes. But this actually using mono depth to recover the discontinuities in depth turned out to not work super well because neural networks tend to be contractions, and so they tend to induce smoothness, and smoothness is antithetical to range discontinuities. So we ended up learning just a straight up gap sensor. And so if I let this go, you can sort of, so blue this is in simulation, and so we can actually compute the ground truth range discontinuities that represent gaps, and the orange is the inference process, and you can see that it's not bad. We miss a gap here that's really, really far away, and we were hallucinating another gap here, but on any given frame, we may not have perfect perception of the range discontinuities, but we can actually use the range discontinuities estimated over time. We can essentially do smoothing, and we can infer a very low-level geometric representation of the environment that allows us to explore it efficiently and that allows us to rely entirely on perception system. So this particular video here is maybe not as instructive. So this is an example of the vehicle driving around in building 4 or 6 on MIT campus. Oh, no, excuse me, this is at Sloan. This is at the Sloan School. They have very nice open spaces. And so you see the vehicle driving around here, and what it's doing is it's recovering the structure of the environment in terms of discontinuities. And you see vertices being placed in places where range discontinuities manifest themselves as a function of the underlying geometry. So you might think that we have found a fancy sort of polygonal world estimator. In some sense we have, but one of the nice things about actually using using a learned model for gap discontinuities is we can, for instance, learn to ignore gaps that we think are irrelevant with the underlying structure of the space. So, Steve Laval's gap tree navigation relied on a star-shaped environment, which meant, for instance, you couldn't put a potted plant with a long, thin trunk because that would represent a puncture in the polygon, and the gap navigation tree would fail in that point. We can actually learn to ignore those kinds of things. And we can also fold that in with our learned sub-goal planner. So here's, this is simulation data showing a learned sub-goal planner on the left relative to the naive planner on the right. This is just using RGB data. There's no range data in the raw signal. We're able to recover the range discontinuities and come up with a map. And then this is the same environment in Sloan. And the vehicle is driving around, and it's building a representation that allows us to decompose the environment into things that allow it to do the useful prediction. So this is nearly everything that I want in terms of symbolic representations. But of course, all of this symbolic decomposition, everything I've talked about, has been geometric. And there's a lot more to life than purely geometric information. So 2 other students, Catherine Liu and Martina Stadler, have been, and I'm not going to spend much time on this because I'm basically out of time, but basically we showed that we could actually include not just geometric information, but also metric information in our planning process. So this is less about abstraction, which is why I'm not going to talk about it much today, but we have the ability to incorporate non-geometric semantic information into the sampling strategy. So we can, for instance, take an exit sign, which is not a geometric feature of the environment, it's a semantic feature, and use that to predict that good plans are likely to go through those doorways. And by the way, if you know your plan is supposed to, if you know your plan requires you leaving the building going outside, recognizing where exit signs are is extremely useful information. And so we actually showed that we could learn a mixed geometric semantic sampler that predicted good plans. And here exactly is the video not playing? Oh, it is playing, good. Here we see a vehicle with a relatively short-range geometric sensor, but a much longer-range semantic sensor that's doing things like detecting doors, et cetera. And it's able to actually recognize where, it was able to make predictions about the structure of the environment much more reasonably, and it's able to follow much more reasonable plans than a baseline planner that's basically constantly distracted by the absence of not seeing doorways, et cetera, or not seeing walls. So we're able to do a much better job of predicting where our sensor has failed and this potential just loss of fill-in. We're able to do a much better job of predicting what are trajectories that are likely to get us more efficiently through the environment, et cetera, using faraway information for which we can't have a geometric model, but we can at least perceive what that feature is and use it to guide the planning. So I don't know that there's a lot more work to be done in this particular space, but we have at least a partial answer to what makes a good symbolic representation. We have an idea, and that good symbolic representation is, again, one that preserves the piece-based completeness of task and motion planning and allows us to find optimal plans efficiently. We can, in some cases, learn the relationship between symbolic and metric models for efficient planning in unknown environments. The one thing that I have no idea about is how do we actually acquire new symbols? So if we're going to start building in semantic information, how do we actually acquire new symbols that are meaningful with respect to the environment and plans? This is still very much a big open question, that we're still at the mercy in semantic models of actually having an engineer tell us what the relevant features are in terms of exit signs and doorways, et cetera. So lots more work to be done. But I really think that there's room for a new mathematical theory that allows us to join inference over the continuous physical world, that allows us to learn those representations that also correspond to the human understanding of the world. So in the perception work, we're very much leveraging neural networks to actually help us detect these things, et cetera. Disentanglement is now a thing that allows us to interpret these representations in terms of human understanding. I want to be able to represent the unexpected with it without having seen it. So I've tried to mention my students who, all of this work is theirs. To the extent that I've injected anything, it's been chaos and distraction. And some of this work is joint with Dan Kodijek and his student Vasilis at Penn, and support from any number of places. But I hope, if you take anything away from this, is that there is hope for actually coming up with a formal theory of representation that preserves optimality, preserves guarantees, and allows us to avoid having to hand code a lot of what we have to hand code today on our robots. And I'll say thank you and happy to take any questions.
All right, I think we've got time. We're currently at 5 o'clock, so if you need to run, go for it. But I think we can hold on to the room for a little bit longer. So yeah, we'll start with David.
Can I ask you a question way back in the,
yeah.
I'm blanking the acronym, but the very first thing.
The factored orbital Bellman tree.
So it seems like you might run into issues in terms of different dimensions of the sets that you're trying to sample.
Yes.
I wonder how you deal with that.
So you have to recognize the dimensionality of the space you're sampling from. And so to a certain extent, that's why we require our striations to be uniformly accessible, because that's a statement that you know the dimensionality of, and it's constant everywhere, and that the sampling guarantees that you can reach the interior of that set. So I don't have a great answer except to say that you kind of have to know what you're doing.
What I meant was like some of the orbits,
Yep.
say maybe dimension 3.
Sure.
But then when you're in contact, maybe you drop a dimension.
Yep.
So it seems like if you're sampling separately or in each of these spaces, then the density of samples may be much higher in one than the other.
Oh, really, really good point. So this is a thing that Will and I, so you're absolutely right, is that you could end up, like if you're not careful, you could end up like oversampling in some spaces, or you could end up undersampling in other spaces. How do you know? Excuse me. So to some extent, the PRM star and RT star algorithms give you tell you how to ensure that. Will's solution to that is to basically sample each piece independently and to think about sort of the guarantees on each striation independently. I don't love that answer because then it precludes you from actually doing iterative sampling and increasing the density when you're having trouble finding plans. So I think maybe the best answer I can give you is like, yeah, it's a little tricky and we don't have an answer.
Hey, thank you. That was really well presented. I
Thank
appreciate
you.
that. I wanted to see if I understood the first part
Okay.
and then ask a question. So when you have a system that's a hybrid system, and so, for example, it comes into contact with the wall, then it has piecewise dynamics
Yep.
that change when you come into contact with the wall. So in order to deal with the fact that it has hybrid modes, you can decompose the space and have the continuous dynamics in one region and the continuous dynamics in another region. And this decomposition is such that each of those spaces has a non-empty reachable set
Yep.
to reach that space. And then you use PRM to sample between how to get from one mode to another mode.
Yes.
Switch between. Okay, for the...
Good.
Thank you. For the example that you gave, that was kind of the culmination of this with all the switches and whatnot.
Yep.
I didn't fully understand what was the non-continuous dynamics there. It didn't seem to be using contact or whatnot.
So the switches make it a hybrid system.
Okay, so you're just considering.
Yes, so the reachable part of the space actually changes depending on which doors are open, et cetera. That being said, something that I also didn't say is that, so again, this is me and Will arm wrestling about the right way to actually do the sampling is like, do you take the striations and order them first, or do you actually plan across each striation and then compose them in the right order?
Yeah.
And my strong preference would be to plan across the striations first, then figure out which are the ones you have to sample inside. The downside to that is that you actually might be wrong and have to resample in lots of places. So I think this gets back to David's comment is like, I am sweeping some details of the sampling process under the rug, but it is a hybrid system by virtue of the discrete mode switches and the actual switches and what reachable parts of the space.
And okay, so then for the decomposition,
Yep.
this is still either user-defined or you hopefully in certain experimental tasks you can decide that walls automatically become part of the decomposition.
Well, maybe. So if I can get this thing, so if you have a dynamic model, and it's really hard to solve a robotics problem without a dynamic model, then you've probably somewhere written it down like this. And this, you can start with this, which is presumably a chunk of Python or C++, and use that to actually do your decomposition. So it's not just like being smart about it or user-defined. Is that the actual whatever you chose to describe your system probably certainly gives you the piecewise analytic constraints, and it probably is also the starting point for uniformly accessible striations.
So for example, the case where the contact changes the dynamics, you would have it written down.
You would
like
have it
this,
written down exactly like
and
this,
you would
yes.
then infer from that that therefore all obstacles are part of a decomposition in which it switches into this.
Dirty little secret though. So that's exactly right, but oftentimes we forget stuff inside here. And so then the thing still you can't find a plan, and they're like, why can't I find a plan? It's like, oh, I forgot a mode or something like this. So you do have to get the dynamic model correct.
Okay, thanks.
So for this last question that you raised about, how to find the symbolic objects that you want to look for, it's sort of tempting, in the interest of leveraging other people's work, just take, the ImageNet categories and throw that into your planning algorithm. It's, they're not going to be, it's looking for baboons, not hallways.
Yes.
Right? So it's not going to be really the right things, but it'll have some of the right things, and it might really help. And you wouldn't have to kind of do anything.
So I more or less completely agree with that. So there's the operational, where do these things come from? And the answer is often, like so many questions, Google. But there's also well, how do we know when we have the right answer? And that is that guarantees optimality. And that is a question that I'm also interested in. So I think it depends. But you're absolutely right. It's like it is perfectly reasonable for me to just throw, as you say, all ImageNet or all the things that the internet knows how to recognize. Use Google Vision or whatever, and just start building those representations. That's the thing that we're thinking about for sure. But it's a little bit dissatisfying.
So you brought up this really good point that basically, as soon as you're uncertain about where things are in the world, you don't know what your topology is, and we don't know
Yes.
when you don't know where your topology is, the notions of optimality break down very
Yes.
quickly, right? So, kind of perhaps maybe the most naive thing to do would just be make a much bigger topology, sort of topologize over all of the different worlds you could encounter. But on the other hand, at the end of the talk, you sort of been speaking about maybe we don't have to sort of reason through all that space. We can sort of pull out sparse things in our world. Do you have any thoughts on how to sort of go from these sparse representations and project that down to more formal space? And that's a very difficult problem. So I don't expect much of an answer there.
No, it's a great question. I wish I had an answer. I've been thinking a lot about it. To your point about topology, so Florian Picorni, Ken Goldberg, and somebody, I forget who the third author was, had a paper on relative homology. And I have a feeling that there's a relationship between relative homology and the striations that we found in the first part. So you can recover relative homology from perception. So the question is, can I actually show that relationship? I don't know the answer to that, but I think there's something there, and I just don't know what it is.
Sorry, can I ask another one?
Yeah.
So I actually have two really quick ones. So first is, what's wrong with range sensors?
They're heavy. They draw a lot of power. They can't see very much. And so I guess I'm a little bit contrarian sometimes. And so everybody is like thinking about range sensing, and like if it's not a laser rangefinder, it's a stereo sensor or an RGBD camera. Like, I just want monocular camera. That's all I want. And so like everybody asks me like, this is a really bad way to solve this problem. Like, I know, but I'm an academic. And so let's try and understand it. It was super interesting to me. It was like all the things I thought would be hard about navigating with a monocular camera turned out not to be hard. And I did not at all see coming the things that turned out to be hard. So what I thought would be hard would be feature tracking. And feature tracking is actually not that hard. Even on relatively what appear to be textureless walls and things, we actually can do a pretty good job. What we can't do is we can't track features through high rate maneuvers. So like if you turn your head really fast, you essentially are blind during that period. And that's certainly true of quadrotors, except quadrotors are high rate maneuver vehicles. And the other thing is that the field of view kills you. So a single forward-facing monocular camera is really, really hard. And so we've been looking at, okay, well, maybe that was just a little bit too academic for words, and we should at least try a omnicam or catadioptric lens or something like that. So that's sort of where we are right now. But I kind of like the part of being an academic is you get to take questions that people are stupid and are like, no, really, we're going to answer it. So you said you had another question.
Yeah, it was the angelic idea.
Yep.
I remember hearing about this maybe from Will actually, but anyway, it reminds me of branch and bound. Is this?
Sure.
Okay, like with upper and lower bounds.
So yes and no. So there's clearly a relationship, but what branch and bound doesn't necessarily do is guarantee that you'll never have to explore some part of the space. It's just going to, whereas angelic semantics, if your upper and lower bounds are admissible, then they will guarantee that you never have to consider another part of the search space again. So the requirements that make branch and bound work are therefore less stringent. So you can have non-admissible heuristics in branch and bound because you have the ability to recover from a bad heuristic estimate. Angelic semantics is a hard commitment that like this is, I know this is strictly worse than anything that I could do over here. So this is now gone from my search process. So the heuristics have to be admissible. Okay.
Can you explain to me, like in the 2-year-old, how you get useful upper bounds? There was something about in a maze.
Yeah, so.
There was something about, I don't know, something being convex. And
Yeah.
you have a bunch of convex stuff. And
So if I have an environment that's punctured, it's a convex set punctured by convex obstacles, then the upper bound between any 2 points is going to be the given by the circle, right? So the biggest distance I can go inside that circle is given by Young's theorem, and so I can work out an upper bound there. Like, it can't possibly be worse than, you know, whatever I have to do inside that circle. So that's one possibility. But it's the restriction to a convex set punctured by convex obstacles. Topology can give you an upper bound as well. So, you know, so the trivial case that I gave when I was giving the slide earlier was that, like, if two sets are disconnected, then the upper and lower bound are both infinite. But you can also apply upper bounds as well. It's like, if I know the maximum size of the space of each subdivision inside my topology, I can work out an upper bound and what the longest path must
I
be.
might have to traverse one of them
Yeah.
fully and then
Right.
another one fully.
Yeah. When you have cycles, it gets complicated. So all of this assumes, and that was, I mentioned it just super briefly, is that we have to take care to avoid cycles.
So I was actually kind of curious if you could talk about some examples for partially observable switched analytic systems.
Not even a little bit.
Okay, never mind then.
Sorry. I had a master's student, so I didn't actually mention, I think, uncertainty at all during the talk. And all of this assumes not just full observability, but deterministic dynamics. And so I had a student, Charlie Guan, who tried to generalize this to non-deterministic dynamics for, like, noisy manipulation, peg and hole. We made a little progress, but it's hard.
Got it. Okay, well then I'll go back down to my fallback question on, do you think, like, when you think about scaling this up to things like the PR2 size, like,
Yep.
size of dynamics, right?
Yep.
So 2 7-DOF arms.
Yep.
How does that kind of, like, where do you see the main challenges in making those connections and leaps?
So good. I see the main challenge is, so I think for the PR2, you wouldn't want to solve the motion planning, the low-level motion planning problem, you know, naively. So the main challenge would be, like, how efficiently can you solve the individual motion planning problems induced by your striations? So we're working with Dan Kodacek and to apply some of this to the Minotaur, which, if you don't know what Minotaur is, it's basically a bounding quadruped. And so it's, you know, it's certainly more than 6 degrees of freedom. And we're trying to apply this to that. And again, how we solve the underlying motion planning problem is actually being solved by Dan's group, and we're solving the higher level planning problem. And so hoping to have something interesting to say there. But I think that's the challenge, is, like, if your system is really, really complicated, then the underlying motion planning problem can be really bad, and you've got to figure out what to do about that.
Can I piggyback on that? I know you said that you don't know anything about it, but kind of switching just to the estimation side, if you had to estimate the modes that you're in, what changes? Can you just teach us? Basically, you've done a lot of work on estimation in general. If I were to run a particle filter over a hybrid, one of these hybrid, you know, discrete continuous things, what should I be prepared for?
A life of pain.
Why?
So think about what happens when the dimensionality of your distribution changes, right? So there's a bunch of things that can happen. So number one is, like, so I spent a bunch of time trying to get some students to work on this, and without success, is, like, the number of samples required to fill spaces of different dimensions. This kind of gets back to Dave's question. Is, like, the number of samples required to fill spaces of different dimensions is bad. And so so imagine you're actually trying to tell which mode you're on, and they're modes of different dimensions. That's a really, really hard problem, because your probability of mass on the lower dimensional system is going to make you think that you're on that lower dimensional system, even though they might be equal probabilities. That's one thing. Another thing is, like, you know, these hybrid systems, when you leave a mode, estimators tend to really not like that. So particle filters might not do that badly, but certainly common filters really, really don't like the case where, like, you've got a hard constraint over the probability of mass and it falls to 0. So there are things like the truncated interval common filter that you can try and get working. It's not great. Leslie and Tomas had a grad student, Patrick Brannigan, who his PhD thesis was actually trying to do estimation on these switching hybrid systems. He had some interesting things. So his work, I think, represents the best that I know about that, but it's by no means a solved problem. You're welcome.
Do you have any other lingering questions? Oh, yeah.
You have a slide mentioning open questions of learning relationship between symbolic and metric models.
Yeah.
Do you mind expanding on that a little bit about the concrete problems?
Well, that was the sort of the last part of the talk, which is that learning the relationship between these sub-goals that are extracted from the gaps and the underlying geometry. So that was my best attempt to answer that question, but there's obviously a lot more that could be said.
Thank you.
So if there are no more questions, can we thank Nick again?
Thank you all very much.
And thank you guys all for coming out.